Good morning, good afternoon, everybody. It's a great pleasure to have you here, and I'll start introducing myself. My name is Teodoro Laino. My pronouns are he, him, and today, together with a stellar team, we would like to give you an overview, an introduction on a fantastic piece of work, collaboration that we have been doing together with Thieme Chemistry for retraining language models with high quality data. So I'll start immediately jumping into the agenda, and also after the agenda, introducing to you all the people that will be with me today. And during the presentation, during the discussion, feel free to post your question in the chat, and we will reserve 10-15 minutes of the time at the end for going through the Q&A. So I hope you will enjoy. Let's start with the agenda for today. So I will very briefly introduce as I said, all the people that are with me. Then I will hand over to Fiona and Sasha from Thieme Chemistry for understanding a little bit more the quality, the data that is behind this project that we have been using for retraining the language model. Then we will give you a very short introduction, overview of the language model themselves. And finally, we will deep dive into the execution of the retraining of the language model with Science of Synthesis and Synfacts. So we will really try to give you a comprehensive summary of the execution of this collaboration. So I would like also to call on stage all the people so that we can go through a quick roundtable of introduction. So maybe I'm asking if it's possible to have everybody on screen. So it's with me today, Fiona Short-Hernandez. Fiona is working for Thieme Chemistry. We have also Sasha Ausberg, working for Thieme, Philip Schwaller, and Alain Vaucher from IBM Research. So I will leave to them to just share each of you. I think we can safely start. I will hand it over to Fiona. Fiona, we are very much looking forward to the content and understanding a little bit more shortly the nature of the data and the operation of Thieme. Thanks.
Okay, thank you, Teo, and thank you for that nice introduction. So I'm going to share my slides now. Can you see them okay?
They are coming.
Okay. I'd just like to say thank you to everybody for joining us. This is really great to be able to discuss this collaboration. I'd like to say a little bit about Thieme and also the products that are involved in this collaboration and some of the reasons why we're doing this. So Thieme is an international and well-acclaimed medical and science publisher that was founded in 1886. So the headquarters is based in Stuttgart in Germany, and it's very well represented internationally as well, with several different locations, including Beijing, Delhi, Rio de Janeiro, and New York. Just move to the next slide. And Thieme Chemistry is a part of the Thieme group. So it's a team of mostly PhD chemists. We specialize in organic synthesis, and we work very hard to try and help chemists to acquire the knowledge that they need to devise synthetic strategies. And for this particular project with IBM, we used two products. So one was the Science of Synthesis database that has been curated over 20 years and is a synthetic methodology database on organic and organometallic chemistry, and also Synfacts, which is our Highlights in Chemical Synthesis journal. Some of you may be aware of some of our other products, for example, Synthesis and Synlet, our flagship journals, and indeed our editor-in-chief, Professor Ben List, won the Nobel Prize in Chemistry this year, which we were very pleased about. We also have open access journals, so there's SynOpen and Organic Materials. We have a number of different databases, for example, Pharmaceutical Substances, which has active pharmaceutical ingredients, about 3,000 of those that are structure searchable. We have a German chemical encyclopedia called RUMP, and some monographs as well. So some of you may be familiar with the Kuczynski Protecting Groups monograph. And of course, we're known for the Select Crowd Review innovation for peer review, which was founded by Ben List and also FileStage and Thieme. So that's a little bit about the Thieme chemistry portfolio. And so if we come now to the collaboration with IBM and why this was important. Well, we knew that the IBM Reaction for Chemistry platform was already a really very good platform, but to date had been using patent data rather than any other kind of curated data from publishers. And so for us, it would be interesting to find out if we combined the AI from IBM with the high quality data from Thieme and from Thieme chemistry, whether we could provide useful predictions for chemists, and also whether we could get a better adoption of that technology so that chemists would use it in their daily work. And also for Thieme, it was very important for us to find out how valuable our data was. So it's been curated over many years with a great deal of care and effort. And so how valuable is the structured data, the Thieme reaction data that we have? And we were delighted to be able to win a number of very important research groups in the fields of medicinal and natural product chemistry to work on this project and to give feedback on the retrained models. So Margaret Brimble, Alois Forstner, Karl Gardemann, Ang Lee, Christina Nevado, Richmond Sarpong, and Dirk Trauner have all been involved. And some of their students have been involved as well. And they've been giving feedback. So there's been 2 rounds of feedback so far, and we're coming to the end of the second round of feedback. And indeed, some of their feedback has already been incorporated into the IBM Reaction for Chemistry platform, which is really great. And we'd hope that there'd be an academic paper then at the beginning of 2022, which Thea will organize together with all of the experts. So just like to show you what a typical Science of Synthesis review contains. You can see Science of Synthesis at sos.thieme.com. So there's usually an introduction and a background. There's a discussion of the methods. There's a synthetic scheme, scope and limitations are discussed. And then we have an experimental procedure so that if the researcher doesn't have access to the primary literature, that particular journal, they can still get started in the lab with the procedure. And of course, if they do have access to that primary literature, then they can link out to that as well through the product. So we have an editorial board with chemists from industry and academia, very eminent chemists on that board, and they recruit the volume editors for particular areas in chemistry, so specified fields, and they then recruit or commission the expert authors to write the reviews in that field. So to date, over 20 years, about 3,000 authors worldwide have been involved with the project, and they're supported by a professional editorial office with PhD chemists that edit and take a great deal of care with the scientific editing for the different reviews. So just showing you a little bit about the actual structure of the data. So Hub and Weil is included in the electronic Science of Synthesis database. It wasn't included in this particular collaboration with IBM. But it is searchable by PDF in the database. The content that we used for the IBM project included the original edition, which was 48 volumes published between the years of 2000 and 2010, and also the update volumes that then started in 2010, where we decided to go through and determine which fields were progressing more quickly, and together with the editorial board, and ensure that they were kept up to date. So in 2010, we also started with the reference library and special topics. So topics of interest to the organic chemist. For example, more recently, we finished volumes on click chemistry by Floris Riches. So he's been the volume editor and put together a multi-author work on that particular topic. And the same for electrochemistry with Lutz Ackermann. And so we have all of these special topics, and quite a diverse range of chemistry is covered in Science of Synthesis. And on the right-hand side, you can see how the information is presented within the electronic product. So it's very structured. It's organized according to the product class or functional group to be synthesized, and in different categories. In the electronic product as well, it reads very much like an ebook library, and it's very easy to navigate. So the content is very structured. Synfacts is our Highlights in Chemical Synthesis journal. It's been published since the year 2005, over 12 issues, or there are 12 issues per year. So essentially the primary literature is evaluated for chemical synthesis by experts, and they enrich each Synfacts with their comments and insights. So there's a very concise presentation of the content, and it's very helpful in preparation for group lab meetings, or if you've got an exam coming up or an interview. And it also helps provide inspiration and generate new ideas. And it really helps you to keep on top of the scientific literature, which is actually something that is very difficult to do nowadays, which we all know. And for the IBM project, the issues that were used were from 2017 and 2018. And these are the categories that are covered in Synfacts. So I think most of these categories were covered, so natural products, also organo and biocatalysis. In this particular project, peptide chemistry and flow chemistry won't have been indexed, but these are the categories that are available. And again, you can see it's a very diverse range of chemistry that is covered, which is also very useful for the training of models. So the more diversity, the better. And this is an actual sample of a Synfact. So every month, there's a Synfact of the month, which is available for free in each of the categories. So if you want to see them, they're open access. And you can see there is a schematic presentation of the entire synthesis of an alkaloid natural product in this case. So you can see the strategy that was used by the research group, and there's actually the reference to the original literature there. And there's also a comment on the significance of the synthesis and the alkaloid, as well as a comment on the strategy used. So it's interesting that we've used, with Science of Synthesis, the information about individual reaction transformations, so going from A to B. And with Synfacts, we've got the more holistic approach, where you've got the entire strategy. So this is the content that has been used in the IBM collaboration. And now I'm going to hand over to Sasha, who'll talk to you about the data in a little bit more detail.
Thank you, Fiona. Good morning, good afternoon, everyone. Thank you for joining our seminar today. My name is Sasha. I'm the Director E-Products at Thieme Chemistry, and I'm going to give you a bit more background on the data set that has been used in the course of this collaboration. So how did we produce this data set? Of course, everything starts with the authors who hand in their manuscripts, and those go through the usual workflow in editorial production typesetting. And what we get out is an XML file, a PDF version, a rendered one, and ChemDraw files, which represent the actual schemes, the chemical schemes from both SOS and Synfacts. And those three file types go to an external vendor, which then processes this data and creates an SD file and an RD file, which contains the single molecules and the reaction data abstracted from the chemical schemes. We get those back from the vendor, and we have an additional QA step to check the quality of the data and make sure that the data is up to our internal standards. If this check is successful, then everything goes to our electronic product, so ESOS. If not, then it goes back to the vendor for another round of corrections, and then those are checked again. So we really make sure that we have high quality data here before we ingest it into the actual product database. And within the product, the SD files and RD files go into the chemistry search, where we can search single molecules and reactions, and the XML and the PDF go into the text search and are available in the online product. And this is done for every single update. We usually have 4 updates for Science of Synthesis per year. So the number of reactions per year that gets added to the database is around 10,000 reactions. And this is done for both the knowledge updates and the reference libraries. If we look at the data sets of science of synthesis and of Synfacts, the number of reactions for science of synthesis is approximately 450,000. For Synfacts, we have 16,000 reactions. Fiona also already mentioned that for Synfacts, we have access to volumes 2017 and 2018 so far. We are currently looking into abstracting the other volumes as well. So the number of reactions for Synfacts will probably increase in the near future. The diversity for science of synthesis is very high because it covers the whole of synthesis, of chemical synthesis. For Synfacts, it's really the focus on total synthesis, as Fiona just showed in an example. The curation is manual or semi-automatic for both products. So as I mentioned, it's a really high focus on quality to make sure that we get a high quality reaction database in the end. We have all the molecules, so reactants, products, solvents, catalysts, reagents for both products. We have yield for many reactions, also conditions. And for Synfacts, we have the literature reference both to the Synfacts article, but also to the primary literature. The data format is an unmapped RD file. We usually have single-step reactions, so we don't have multi-step reactions, which is quite handy for this particular use case. And all of the reactions come with 2D coordinates. So this gives you a bit more context on the data set that has been used in the course of this collaboration. And with that, I want to hand over to Philippe, who will go into the details of the AI model. Thank you.
Hi, everyone. I'm Philippe Schwaller. I'm currently a postdoc at IBM Research, and you can now see my screen. I will give you a brief overview of the technical background of the artificial intelligence models that we use to model the language of chemical reactions. The data we started working with is USPTO data, so extracted from patent by Daniel Lau, who made available a huge data set with millions of chemical reactions. One way to represent them are reaction smiles, a line notation developed in the 70s. And here is the corresponding 2D depiction. If during my talk I mention atom mapping, what I mean is that every atom in the product is mapped back to the corresponding atom in the reactants. For the next few minutes, this will be the representation of choice because it allows me to represent atoms as letters and molecules as words. And then after splitting those smiles into sequences of actions of atoms, I can borrow methods developed for human languages and apply them to problems in chemistry. Our go-to model is the transformer model that was published by Vaswani et al. For neural machine translation, where the goal is to learn a translation from, for example, French, le chat est noir, to another language like English, the cat is black. And similarly, we can map the reaction prediction problem, where we try to predict the most likely product given the precursors as a neural machine translation problem. We've explored this idea when I was at the University of Cambridge and published a molecular transformer. And this model, without integrating any rules or chemical knowledge, was able to accurately predict unseen reactions on benchmarks datasets and work better than other approaches. When I went to the University of Bern, we asked the question, what is missing in reaction prediction? And one weakness that we observed was stereochemistry and the other experimental validation. And that's when I teamed up with Giorgio to work on carbohydrates reactions. Giorgio performed the 14-step synthesis of a lipid-linked oligosaccharide. And on this test set and two other test sets of carbohydrate reactions, we saw a huge accuracy increase using transfer learning. This is one example of a glycosylation reaction that the model was able to correctly predict, which is non-trivial even for human experts. Transfer learning, so training on multiple data sets simultaneously, can be applied to any reaction subset of interest, and this is a really nice thing. Another topic that we explored is multi-step synthesis planning, and this was with the University of Pisa, where we trained 2 different models, one to do a retrosynthetic prediction, so going from the product, from the target back to suggestions of precursors, and to rank the different paths. We used a forward prediction model to get information of how to navigate through those different routes. What we do differently compared to other approaches is that we not only predict reactants, but also reagents, catalysts, and solvents simultaneously, if you compare this to what is typically done in the literature. In this first part, I've shown you sequence-to-sequence models that use a reaction transformer for reaction prediction and also retrosynthesis. In the second part of my brief presentation, we will focus on encoder-only transformer models. This is another type of transformer models that takes in a sequence. In our case, we will use chemical reactions, the full chemical reaction, and then this can be used to either predict reaction classes or regression tasks like yield prediction. If we take a reaction classification as an example, then what I mean by that is like predicting the most likely name reaction corresponding to a chemical reaction represented as a reaction smiles. And on data from NextMove software, we could show that we were 98% accurate. What is even more exciting for me for those reaction encoder models is if we take away this last layer and take only the encoder part, we get back as an output data-driven fingerprints that encode all important information of those reactions. And using those fingerprints, we were able to map chemical reaction space. This can also be used to search for similar reactions. For example, if we do a new prediction of a Diels-Alder reaction on IBM Reaction for Chemistry, then after getting back the prediction, we can really go back to the training data and look at what were the most similar reactions to the predicted reaction. Here you see the other Diels-Alder reactions, and what is also very useful is that we can display additional information and have even a link back to the original documents. So chemists would have access to conditions and procedures that he or she could try to make the predicted reaction run. One question that always bothered us is why do those transformer work so well? And this is work published with Ben Hoover and Hendrik Strovald in Science Advances, where we trained an encoder model on millions of reaction smiles and then visually inspected what it had learned. And what we discovered is that our model learned atom mapping. What is atom mapping? Or what does reaction mapper do for you if you have an unmapped reaction like that? The reaction mapper can provide you the atom mapping and connect the product and precursor atoms. On an independent benchmark, reaction mapper was ranked the best atom mapper, and it's even better than commercially available tools. And compared to the other open source alternative, it's a huge difference. So I'm already finishing with my summary. In the first part, you've seen encoder, decoder reaction transformers for reaction prediction and synthesis planning. And in the second part, I've introduced you to encoder-only reaction transformer models for classification fingerprints, reaction yields, and atom mapping. And if you're wondering what's next, just one quick slide on RXN. Imagine you're a chemist at home, you do the creative process to design a molecule. Then you connect to the cloud where you get access to a synthesis planning tool. But not only that, you can convert all the individual steps into sequences of actions that you could then perform in the lab. But also, if you have a cloud-connected synthesis platform, you could automatically execute those actions on a robot. And this is a bit the vision and the prototype that we have at IBM Research in Zurich. And what is crucial for that is high quality data. So that's why this collaboration with Thieme is super important. And now I will hand over to Alain.
Thank you very much, Philippe. Hi, everyone. My name is Alain Rocher, and I'm a research scientist at IBM. And in this last part of the webinar, before the questions, I will go into more details about how we combine the AI models from IBM with the high-quality data from Thieme. So without further ado, let me start with the first topic, because there's a lot of information that I really want to convey to you. So let's start with the generation of the training data. As you heard from Philippe earlier, the AI models that we use rely on the reaction smiles notation, where we consider a chemical equation with the product on the right-hand side, and on the left-hand side, all the precursors, including the reactants, solvents, reagents, and so on. So in the end, this is the format that we will want to extract from the Thieme data. As you heard earlier, we had at our disposal in this collaboration documents from Science of Synthesis and Synfacts, which you may know best in the PDF form, as you see in this screen. But as you heard earlier from Sasha, there is also more structured information on this. So let's look at an example from SOS. We also have access to XML files that contain the structured information from all the document except for the images. Then for the reactions, we have access to the two-dimensional structures and properties of the reactions in the RDF files. If we look in more detail at one of those reactions, here we see that we have one reaction that is generic in the sense that it is not fully explicit in terms of atoms, and we have three more specific reactions corresponding to that generic reaction. In the RDF files, this ends up being 4 separate records of reaction. And what we need to do here is to combine the information from the generic reaction with the information from the specific reactions. And this is where we need the information from the XML in order to put this information together. So in summary, we end up using the RDF files for the chemical structures and the properties, and we determine the context of the reactions from the XML files. In the end, what we start with are roughly 76,000 documents from Science of Synthesis and 2,500 documents from Synfacts. Starting from this data, we will go through several steps to generate the training data that we need in reaction smiles format. So first, we will extract the reactions and convert them to reaction smiles. Then we will standardize the reaction smiles in order to harmonize the data representation. And in a third step, we will go through some sanity checks to discard reactions that we don't want to include in the reaction data. I will shortly go in detail about each of those 3 steps. So for the first step, we extract all the reactions from the Thieme data, which leads us to roughly 450,000 reactions. Out of those, some will not be usable because they are generic and they contain R or X in the structure, and some of them will fail the chemical structure checks, which then leads us to a total of roughly 380,000 reaction smiles that we then start with. We then take those and standardize them in order to harmonize the data. I'm not going to go in detail here, but this will include canonicalization of the reaction smiles, removal of isotope information or duplicate molecules, and so on. After standardization, we go to the sanity checks, where we will discard reactions that we don't want to include in the training data. This includes duplicate reactions or reactions with more than one product or less than 2 precursors, reactions where the product contains atoms that are not present in the precursors, or reactions where there is too much formal charge, and so on. In the end, this leaves us with 330,000 reactions that we have in our training data. I want to shortly comment on the numbers here. So we saw earlier that we started from 480,000 reactions that were extracted, and here we end up with 330,000 reactions, meaning roughly a portion of 70% that is usable. It may sound like a lot of reactions are being discarded, but this, in fact, this number is quite to be expected, and it is also much better than, let's say, in the patent data, where we discard not 30% of the reactions, but more in the area of 70%. Having said that about the generation of the data, the next step is to train the models. As you saw before with Philippe, we rely on a sequence-to-sequence model based on a transformer architecture. And in the context of this collaboration, we retrained 2 models. We retrained the forward reaction prediction model, as well as the retrosynthetic prediction model. Fiona mentioned in the beginning that we had 2 rounds of training, after each of which we got some feedback from the experts, which I will also go more in detail later on. The data, the actual data that we train with, comprises not only the science of synthesis and the Synfacts data, but also the patent data, because this patent data helps the model learn the syntax of the reaction and also improve the accuracy of the models. Then, starting from this data, each model takes roughly 2 days to train. And then, when the models have been trained, we can analyze the performance on a set of Thieme reactions that were not part of the training data that we put aside just for this purpose. If we take the model trained on patents only and evaluate it on the Thieme dataset, we end up with roughly 22-23% accuracy. And when we include the Thieme data, we increase this accuracy up to 69.5%. And I also want to mention here that if we train only on Thieme data without the patent data, this number will be a bit lower, around 60%. So it really makes sense to combine all the information that we can have. On the retrosynthetic task, the accuracies are a bit lower because there is not only one correct answer, but still it makes sense to look into those values. So for the patent-only model, we have 1% accuracy, and this increases to 17-18% accuracy when combining also with the Thieme data. Now, I will go back to more examples a bit later in the presentation. But first, I wanted to mention a few challenges of extracting new data and training models on it. And some of those challenges we could solve during this collaboration, and some of them will need a bit more time to fix. The first challenge that we had was that in the first generation of the model, many reactions were discarded because they contained more than one product. And as I mentioned earlier, this is one of the filters that we have. So in order to still include this information in the data set, we went into the information of the tables when they contain information about ratios or yields, enantiomeric excess, and so on, which allowed us to extract 10,000 more reactions for the training set. Another challenge that we had was that for some reactions, some of the reagents were present as names, but not as actual structures. So to solve this issue, we generated an additional name mapping of roughly 750 names in order to get on the order of 6,000 additional reactions. And in this case, we extracted as many names as possible, but sometimes when the names are in the tables with specific column names, we couldn't do this until now, and this will need some more work. Another issue that is present in any data set is the representation, especially when one has organometallic compounds because of the different types of bonding and so on. And in the example shown on this slide, when we extract the structure, it ends up adding a hydrogen atom bonded to the phosphorus atoms, which is not correct. And also, in this specific example, the standardization will fail because of the incomplete or the hypervalent configuration of the chlorine atoms. Now, in the next few minutes, I would like to go into some of the feedback that we got from the experts. After the first round of training the models, we got a first round of feedback, which was overall very positive, in the sense that there is value added by adding the Thieme data into the models. Still a few issues, such as bias towards specific reaction classes that are more represented in the data, or maybe issues with stereochemistry sometimes, or also when looking at automatic retrosynthesis that they are not successful. And in the next 3 slides, I will also mention some additional feedback that we then included for the second generation in the models. The first one was mentioned earlier by Philippe, which is that the experts saw value in being able to find related reactions, which we didn't have at the time of the first model generation. And in order to help in this regard, we added some functionality to be able to look for related reactions from the training set or from the pattern data to better rationalize the predictions that are being made. Another comment was the lack of variety. And in here, I don't want to go into too much detail, but you can imagine that the reactions present in the data set occupy a large area of reaction space. And for the second generation of the models, for the retrosynthetic models in particular, we force the models to make predictions from different areas of the reaction space. And the third bit of feedback that we included was to add the possibility to specify photochemical or thermal reactions with the help of an additional option on the web interface. So with this, and also with the improvements in the data generation, we then produced a second generation of models, and this led to a second round of feedback by the experts, which was also positive in the sense that the new models were better than the first generation, more varied reactions, and some classes of photochemical reactions that worked well. I want to show you in the next slides also some concrete examples of feedback. The first one is about a deprotonation reaction where only the second generation of the Thieme model was successful in generating the correct product that was also observed in a publication. In a second example, similar thing where it is about the retrochemistry of a hydroxylation reaction where only the latest generation model was successful to predict the correct regioisomer. In the third example, the expert looked at a full retrosynthesis and mentioned that the version 2 model using Thieme data was able to propose steps that actually reduce the complexity of the target molecule. There are also some more negative bits of feedback because the models, they don't work well for all kinds of reactions. And one example are the so-called 4 mysterious reactions of Woodward, where only 2 of them were predicted correctly and 2 of them were predicted incorrectly. And when the predictions are incorrect, it is then helpful to look into the closest related reactions in the training set or in the available reactions. And doing so in one of those cases shows us that the closest reactions actually come from patents. And looking a bit more into it, this raises a few questions about the quality of these reactions. In another example of a multi-step retrosynthesis, the algorithm wasn't able to actually simplify the molecule. And this is something that is an ongoing effort in the team that we didn't look in particular during the collaboration, which is to get a sense of the strategy for the disconnections to be made. And here is a last example of feedback where there were a few issues with predictions or not being able to make suggestions that the chemists would come up. And in this sense, this is mainly related to the availability of such reactions in the training data. So as you see, it's often about data. I don't have a lot of time to go into the examples, so I will skip some of them, especially for the forward predictions. And instead, I will show you an example of a retrosynthetic prediction as is being used from the user interface that we have. So in this case, I entered a compound that I wanted to do a retrosynthetic prediction for. I selected the latest version of the Thieme retrained model, and then launching the AI models in the cloud. This enables us to look into the different suggestions being made by the models, as well as the closest reactions to those records. And basically, I am at the end of this part of the presentation. And before I finish, there's one more thing that we all wanted to mention, which is that the retrained Thieme models will be made freely available from now on until the 4th of December. So anyone, anywhere, can go on the IBM RXN website and test those models until Saturday noon. With this, I would like to thank you for your attention, and we can proceed to the panel and Q&A.
Thank you, Alain. Thank you, Philip, Fiona, Sasha. I think this was really a very entertaining and also clarifying discussion about the nature of the collaboration. We have quite several questions in the chat, so I will briefly go through those ones, but I think it's important to remark because it has been really an example. What we have been able to do with Thieme, and actually even the possibility to make the models retrained with the Thieme data available for 3 days starting from now for everybody freely on the public platform. Please go there, test it yourself, do comparison with the patent data, and beyond what you have been listening, you can make up your own mind and judgment on how quality data is impacting the learning of language model for organic chemistry prediction. So I would start with the first question for Sasha. I think this is more or less what the time when this happened. Maybe either you, Sasha, or Fiona. Let me just go directly to the question. So do you specifically label conditions belonging to, for example, a flow reaction? And do you have specificity for collecting reaction like more for flow reactors and parameters like flow rate? I think probably we can even try to generalize a little bit the question and asking how is science of synthesis clustering all the data? Are there thematic issues connected to flow chemistry?
I can start or try to answer that, and Fiona, maybe you can add to that. So I think this particular question is aiming at Synfacts because Fiona showed there's a cluster on flow chemistry in Synfacts, but this was not part of this collaboration, and I don't think we have it indexed yet. But we can certainly have a look at the available data and see if we can index that accordingly if it's relevant. In general, when you look at science of synthesis, we have to distinguish between the knowledge updates and the reference libraries. So the reference libraries are very specific to a certain topic, and will include some more special information compared to the knowledge updates, which are as Fiona explained, updates to include the most recent developments in a certain area based on the original volumes. Usually we index the molecules as explained before, so reagents, catalysts, solvents, and of course reactants and products, and the conditions to some extent. But I mean, the data is all there, so we can easily modify that and extend the abstraction to other areas of interest.
Yeah, I'd just like to add to that we do have a volume on flow chemistry and science of synthesis. It was put together by Tim Jameson and Guido Koch. So it would be interesting to look at how that has been used in this particular project as well in a little more detail.
Awesome. Thank you, Fiona. Thank you, Sasha. The second question, I think, is for Alain, Philippe. The question is related to some of the metrics that have been shown during the presentation, more specifically 18% for the evaluation of the retrosynthesis. So the viewer was asking, what does that really mean?
Yes, so I can take this one. So those 18% mean that starting from a target molecule from the validation set, when one makes the prediction of the precursors from that, there is an exact match to the reaction that was present in the Thieme record. So it is a good sign in the sense that 20 or like 18% of the predictions have an exact match with the training data. However, this number is a bit low because even changing the solvent or using one equivalent reagent would make this test not pass. And then also considering that there are many ways to make the same molecule, this also reduces this number. There is a metric that we didn't include in this presentation, which is after having done a prediction of the precursors, to use the forward prediction model on the precursors to see if the predicted product starting from this prediction leads to the actual target molecule that we had. And I don't remember the numbers that we had there, but it is, if I remember correctly, around 70–80%.
Cool, thanks. And by the way, I just addressed the person making the question as a viewer, but we have also the real name. So Friedrich Koroll is also asking 3 more questions. So I will go through this question. The very first one is, what about the retrosynthesis of chiral compounds? And probably we can, I think it would be interesting to, if either you, Alain, or Philippe can give a little bit of perspective on the performance of the Thieme based on the feedback that we got from the expert use. That's the number one. So retrosynthesis of chiral compounds. The second question is, does a retrosynthesis always ends with commercially available compounds? And I will go to the third one as soon as we go through the first 2.
Philippe, if you want to go ahead.
Yeah, I can take the chiral compounds. It is always really dependent on the data, and the prediction much improved using Thieme data, at least on the reaction space that is covered. But it is clear that chiral compounds are more difficult than non-chiral compounds. So there's the accuracy will likely be less than for non-chiral compounds.
For the second one, the question about the commercially available molecules, there on the platform that we have, there is a list of compounds that we consider to be commercially available, and this covers, on the one hand, molecules that can be purchased from a chemical supplier. And on the other hand, in this context of the collaboration, we also added the compounds present in the Thieme dataset as being available, in the sense that if one looks them up, one already has the synthesis of those compounds. But this is flexible and depends on the setup of the framework.
Yeah, that's, I think, is a very, very interesting question, probably unsolicited, because this was exactly one of the feedback that we got. We started working extensively with commercially available molecule, but in reality, for the end user, is equivalent whether you can purchase or you have a methodology to make the model. So it's a very good input. The other question always from Friedrich Kohl is actually on how many steps can you predict with the algorithm and how long does it take? What is the performance for a molecule of medium complexity? Maybe Philippe, you want to, or Alain.
Go ahead. So, yeah, so you can go up to 15 steps. We have, I think, a maximum at 15 steps. And how long does it take for a molecule of medium complexity? I would say a few minutes. And then you have different routes, suggested routes to your molecule. What is also really interesting is the interactive mode that we have in the retrosynthesis, where you basically get the prediction and you can also select which of the suggestions you like most, and like that it becomes like a human AI interaction game to build up those synthesis routes.
That's correct, absolutely. And Alain, one question for you. How long did it take to go through the broken reactions and purify all the data set? This is a question from Yu Yang Song.
Thank you for the question. I would say it was an iterative process where we were a lot in contact with our collaborators from Thieme, also to understand the way the data is structured and so on. And then one thing that was helpful was to look into some of the reactions that didn't pass the filters that we have in place and that I mentioned on one slide, such as when there are more than one product or too few reactants or missing atom types and so on. And looking at those examples and then going, like starting from the extracted reaction and going to the PDF allowed us to then see if there was something missing. And this is, for instance, how we detected some of the missing reagents, or how we also saw that in the end it makes a lot of sense to determine the main product of the reaction when we can, and so on. So in the end, it took some time, but it always takes some time to go through a new data set of reactions. And in this case, what was very helpful was that all the information was already in a standardized format that we could extract reactions from. So yeah, short answer.
Thanks. We have two last questions and almost one slightly more than 1 minute to go before the end of the broadcast. So let me ask the question, you, Alain, or Philippe, and it's from Ali. To what extent can we address the issue of the stereochemistry in the model, with the existing model? Maybe I can probably try to frame it. Is this a problem more connected to the models, to the data? Your opinion.
I can take that one. So we can represent stereochemistry to our model as good as it can be encoded in SMILES. SMILES is a line notation, and compared to 2D graphs, it can contain some 3D information like chiral centers or cistrons stereochemistry, and this we can encode. And if we have enough example of reactions that contain stereochemistry, our models can learn how it reacts, how it affects the reactions. Yeah.
And probably also for the people that are listening, also the work that you were mentioning about transfer learning on carbohydrate chemistry is a very good example of how you can bring this model, the language model, to the extreme of molecules that are highly chiral. So that's another good example. I would like to wrap it up with one last question for Fiona and Sasha. I think most of the chemists are today used to exploit and use high quality data in their daily workflow by just doing queries like a database. So what is your opinion in a short time on what machine learning can do for your clients? We have seen in this seminar what your data, high quality data, can do for machine learning. But what do you think is the other benefit of the interaction of machine learning for the end user experience of your customers?
Well, I think obviously it would really help them in terms of innovation and saving time in the lab. And we've seen with this experiment that the data that has been used from SOS and Synfacts is, I think, 3 times better for forward prediction and 9 times better for retrosynthesis against baseline models. So obviously, I think it'll be a massive time saver and a real help with innovation in the pharma industry in particular.
And also, I think, yeah, I mean, our collection is very diverse. We are also available to support a collaboration. So we are the experts on the data, and we can help to customize with a a solution that is valuable for our customers, as we did in our collaboration, for example, as well.
Awesome. So I would like to reconvene all together, and I would like to thank again.
We are also.
Oops, we have a little bit of a return of audio. So I would like to thank again Sasha, Fiona, Philip, Alain, and all the people that were listening. And again, all the Thieme models are available on the RXN public portal. Please go live, use them, and make your own judgment comparing the models between patents and science of synthesis and Synfacts data. And for people that are in another time zone, we will reconvene here in approximately 6 hours, 7 hours. Thank you so much. Thank you, everybody.
Thank you.
Thank you.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.